I'm going to use this example of case B to run through the program very quickly and show how you would use it to compute power. Then I'm going to go back and look at each of the elements more carefully. Now remember, case B is a situation where we have sampling at two levels. We sample schools, and then within schools we sample students. The first thing we want to do is tell the program which metric we're going to be using for the effect size, and we're going to be using the standardized mean difference D, where D is standardized by the total standard deviation. We're going to come back and look at that more carefully in a few minutes. Over here we have the number of levels. Initially the program sets the number of levels to 2. We will stay with that, and we will simply label the levels. I right click over here, and I'm going to call the first level schools and the second level students. I click OK, and these are labeled schools and students. We're randomizing at the top level. We're randomizing schools so that each school is assigned to either treatment or control, and then students are nested within schools. We can see that over here, and we have the option of changing that if we wanted to. Over here we have the number of units at each level, the number of schools, and the number of students. We'll come back to that in a minute. Over here we have the ICC. We saw earlier that that was going to be about 0.07, so I'm simply going to put 0.07 over here for the moment. Later we'll come back to the span of effects, to the covariates, to the statistical model. For now, let me simply set the cost of each unit. We're going to assume that for every school that's enrolled in the study, that's going to cost about $2,000, and for every student that's enrolled is going to cost an additional $50 for follow-ups and so on. The standardized mean difference, let's set that at 0.5. Over here alpha is set at 0.052 tilde. We will leave it at that. Power is shown as a bar graph. We'll change that to be shown as digits. And with this setup, by default the program is showing an opening value of 2 schools for each treatment and 2 students within each school. With these costs, power is obviously only about 7%, and the study would cost about $8,400. The next thing we can do is to figure out how many schools and students we need to get power up to an adequate level. Let's assume that the desired power is going to be 90%. I'll put that over there. We can simply increase the number of students per school and increase the number of schools until power reaches 90%. But the thing is that whereas in a single level design, all that you need to do is to keep increasing the number of students until you reach adequate power. In a multi-level design, we have the option of increasing the number of students and or increasing the number of schools. And there is essentially an infinite number of combinations that will give you the power that you want. One of the things that we might want to do is to find the most cost-effective balance of these two that gives us power of 90%. And the easiest way to do that is to click on this thing over here called the Optimal Design Wizard. We're going to accept all of the defaults. We'll come back to that in a few minutes. We click Compute, and the program tells us that the most cost-effective design would be to have about 11 schools for each treatment with approximately 23 students per school. So we'll paste that information in. We see it over here now. We have 11 schools per treatment, 23 students per school. The total cost is going to be about $69,000. Power is going to be about 92%. Once we've done that, we can create a report that puts all of this information into actually there are 2 reports. One is an executive summary that summarizes all of this, and then after that there's a much more detailed report that goes into a great amount of detail about each of the assumptions that we've made and what those mean, which is intended more as an educational tool. And then finally we'll be able to produce a graph so that we see over here, for example, remember back on the main screen we saw that with power, with 12 schools per treatment, we had power of 90%, and we see the same thing over here. If we click on this point, power is 91.8%. The number of schools is 11 times 2. That's 11 for each treatment. The cost of the study was about $69,000. And down here we see all of the details. This is for a 2-level cluster design. Schools are randomized, students are nested, and so on. Okay. So that's a quick overview of how the program works. Now we're going to go back and look at each of these items in more detail. The next thing that I want to do is to go back and look in more detail at the ICC, which in this case we said was 0.07. Let's take a quick look back at a summary of case B. Again, we are sampling schools, and then within each school we're sampling students. And we've said that the ICC for schools is 0.07. Typically, the way that somebody would get this number, if somebody is working in the field of education, they probably would look at various publications that have been produced that give the expected ICC based on the kind of hierarchy that's being used, based on the kind of outcome that's being used. And in this case, they might see that the ICC is 0.07. In fact, to compute power, that is all that you need. You just need to know that the ICC is 0.07, and you don't need to pursue this beyond that. However, there are very good reasons for understanding how the ICC translates into a span of means or a span of scores. One reason is that rather than simply taking the value of 0.07 and assuming that it's correct, if you can understand how that translates into a span of school means and a span of student scores within a school, you can ensure that the number that you're working with is plausible and that it is consistent with the kinds of numbers that you have come to expect. The other reason is that at some point you're going to want to explain either in a grant application or to other people that are working with you what the ICC means, and we want to be as transparent as possible. And being able to report that the ICC is 0.07 and that it translates into a specific span of school means and student scores and so on allows you to be much more informative. And there's actually one more reason. In this example, we're starting with the ICC, and we're seeing how that translates into different spans. In some cases, you might not have the ICC. You might be working with a hierarchy for which there is no good published data, or you might be working with a different outcome. And so you might have a sense of how the mean varies from school to school or how the scores vary within a school, but you might not know the ICC. And in that case, you can actually start with the span and back compute the ICC, which again is the value that we need to compute power. So what I'm going to show you now is I'm going to quickly review what these numbers mean, and then I'll show you how you can use them inside the program, because the program can do all of these transformations automatically. We said that the ICC is 0.07, representing the proportion of total variance that takes place between schools. Let's take a minute and think about what that means. One thing that we can do is take a look at these schematics. These both are for case B. The one at the top looks at standard deviations, and the one at the bottom looks at variances. In each case, we have 3 rows: the total, students, and schools. Over here, we're looking at standard deviations. The row marked total is a schematic of the distribution of the student scores across schools. The one labeled students is a distribution of the student scores within any single school. And the one labeled schools is a distribution of school means. In other words, if we somehow knew the true mean SAT for each school, and we computed the standard deviation of those means, it would look like this. Again, if we knew the standard deviation of student scores within a school and plotted the range, about 95% of them would fall in this range. And if we come back and look at student scores across all schools, it would look like this. And of course, all of this makes sense. If we're saying that the mean varies from school to school, and then we take the student scores across all schools, obviously that range has to be wider than the range of scores within any single school. Down here we have the variances. This is the variance of school means. Again, if we knew the true mean SAT score in each school, and we're talking in both cases about schools in the control group, if we took a look at that variance, that would be about 700, and we've plotted that over here. If we look at the variance of student scores within any single school, that would be about 9,300, and we've plotted that over here. And then if we look at the variance of student scores across schools, that would come out to 10,000, and we've plotted that over here. Notice that when we plot the 10,000, this is simply the two components added together. This part over here is the variance between schools. This part over here, the light blue, is the variance across students within a school. And as I explained in the text, these two components are additive, so we can simply add one to the other to get the total. Obviously, we cannot do that with standard deviations. The standard deviations are not additive. So whenever we're trying to partition components, we're always working with a variance. Okay, given all of that, I should just point out one more thing, that the standard deviation over here corresponds, of course, to this variance. This is the square root of this, and this standard deviation is the square root of this. This total standard deviation is based on the square root of this whole thing. So if the variance down here is 10,000, the standard deviation is 100. The span is going to be 4 times that, or 400, which we see over here. The variance for students within a school is 9,300. The square root of that is the standard deviation, which we see plotted over here. And finally, the variance for the variance of school means is 700. We take the square root of that and get 26, and that's what we've plotted over here. Now, if we start out knowing that the overall variance of students across schools is 10,000, and we know that 7% of that is the variance between schools, then we can say that 7% of 10,000 is going to give us a variance of 700, which is this. Once we have that, we can take the square root of it and get the standard deviation for schools, which is this. And once we have that, we can multiply it by 4 and get the span for schools, which is this. So working backwards from knowing the overall variance and the ICC, we can come back and figure out that the standard deviation of school means is around 26, which means that the span of school means is going to be about 100 or 106 points, so that if the grand mean is 500 and the span is approximately 100 points, that means that the school means are going to range from approximately 450 to 550. Similarly, once we know that the ICC for schools is 7%, that means that the remaining variance, or 93% of that, is for students within schools. That's going to be about 9,300. The corresponding standard deviation is about 96, which gives us a span of about 386. And that tells us that the student scores within a school are going to range from approximately, I guess, about 310 up to about 690. And the next thing we can do is ask ourselves if these numbers are consistent with the numbers that we generally see. In other words, if it generally would be the case that you would expect that the school means would vary across approximately this range, and that the student scores within a school would vary across approximately this range, then we can be confident that all of these numbers make sense, that an ICC of 0.07 is plausible. Additionally, if we are reporting the ICC, we can also explain how it corresponds to a distribution of school means and a distribution of student scores, so that the people looking at this understand exactly what these numbers mean, and so that they are as transparent as possible. One last point is that in some cases we might not have the ICC to begin with. We might actually be starting with some idea of what the span of the school means might be and what the span of the student scores within a school might be. Working from this and this, we can compute the ICC, and just to sort of draw this out, if we know the span over here and we know the span over here, then we can compute this standard deviation in this one. If we have this standard deviation in this, we can compute this variance and this one. If we have the two variances, we can compute the total variance, and then we can take the proportions, so that we now have figured out the variance here is 700, the variance here is 9,300, the total variance is 10,000. 700 over 10,000 gives us the 7%, which is the ICC. One of the things the program is able to do is that it can work in either direction. If you start off by giving it the ICC and the total variance, it can actually produce this this little schematic over here. On the other hand, if you start off by giving it these spans, or actually by manipulating a schematic so that these spans are reflected in that schematic, it will go back and compute the ICC for you. And the last thing I want to do over here, I was using sort of approximations of the numbers, but we have a table that gives the numbers exactly, so that we can see over here, for example, that the span of the school means we go from about 447 to 552, which is a span of 106 points, and that the span of the student scores within a school would go from about 307 to 692, which is a span of about 386 points. And finally, of course, the standard deviation for students across schools is 100, reflecting a range of about 300 to 700, or a span of 400 points. If we come back to the program now, we can see how that actually looks. I'm going to come up here, click on ICC, show the schematic. One thing I want to do is to change the mean of this so that it's going to reflect the overall mean for the control group of 500. I click OK. We have 500 over here. Then I want to put in the span of the student means, of the student scores, and we said that was a span of approximately 386 points. So let me come back here, and I'm going to set this at 386, and then we set the ICC as 0.07. And using the logic that I showed you a minute ago, the program figures, well, if this is 386 and the ICC is 0.07, then the span for the school means is going to be about 106. And it displays that. And you can see how as the ICC goes up or down, these spans change. Alternatively, if I didn't know what the ICC was, let's say we set that initially to 0, but I come in over here, I can say I want to actually enter the span rather than entering the ICC, and I'm going to say that that span is, we said that was about 106, so let's do that, set that to 106, and when we do that, we see that the corresponding ICC is 0.07. So this works back and forth. Also over here, if I tell the program that I want to enter spans rather than the ICC, it displays the span. I can go back and change it to the ICC. It displays that. So what we've covered at this point is I've tried to give you a better sense of what the ICC means, and critically to show how you can move back and forth from the ICC to the variance to the spans to ensure that all of these values are plausible. This whole exercise, the whole idea of entering an ICC, is what we're trying to do, again, is to describe what the population looks like. And specifically, we're trying to explain how the variance is partitioned, because the point that I keep coming back to, and this is going to become very clear in a minute, is that we can't think about the variance as a total. It's not simply a variance of 10,000 corresponding to a standard deviation of 100. We need to think about it as far as its component parts. 93% of the total variance is light blue. That is that's the error that's coming from students within schools, and 7% of the variance is dark blue. That's the error that's coming from the variance in school means. And what we're going to see in a minute is that we have to deal with each of these error components separately. We're going to deal with this one by increasing the number of students within a school, and we're going to deal with this one by increasing the number of schools. So what we've done at this point is I've discussed how you can partition the variance into its component parts, and how we can use the corresponding values of the standard deviation or the span to make sure that we get that right. Now we turn to the reason why all of this is important. And to explain that, I'm going to juxtapose case A versus case B. Now we're looking only at the variances. Earlier, we used the standard deviation to make sure that we had the variance right, but the standard deviation doesn't matter anymore. In case A, remember that we were looking at students that were sampled across all schools, so there's only one level of sampling. In case B, we sampled schools, and then within schools we sampled students, so there's two levels of sampling. In the population, in both cases, the variance of student scores is 10,000. Over here, it's simply 10,000. Over here, we could divide it into two parts, 930 between schools, 700 between schools, 9,300 within schools, with those two adding up to 10,000. The reason that this becomes important is not when we're dealing with the population, but when we try to draw a sample from that population. When we go to draw a sample, when we're dealing with case A, where we simply were sampling at one level, if the population variance is 10,000 and we draw a sample of 1,000 students, then the error variance in the sample is going to be 10,000 divided by 1,000, which is 10. That's the error variance in the sample. And what happens basically is that every additional student that you add to the sample provides more information, provides more balance. Any single student that happens to fall below the mean is likely to be balanced by another student that falls above the mean. As the number of students approaches 1,000, those positive and negative errors balance out, and we end up with a fairly precise estimate. The variance is 10. By contrast, in case B, let's assume for the sake of argument that we're going to have 20 schools and a total of 1,000 students. As the population variance for students within schools was 9,300. If we have 1,000 students, then the error variance in that sample of students within schools is going to be 9,300 divided by 1,000, 9.3, which is quite small. In fact, I've enlarged it over here so that we can see it on this scale. The error variance for schools, the population variance for schools had been 700. If we have 20 schools in the sample, we take 700 divided by 20, and the error variance for schools is 35. And again, I've enlarged that a little bit over here so that we can see it. But the key thing is that as we continue to add more and more students, what we're increasing is this number over here, so that going from here through here to this little piece of the variance keeps getting smaller and smaller, but it has no impact at all on this part of the variance. It doesn't matter how precisely we can estimate the mean for students within a school. That doesn't do anything to help us estimate the mean of all schools. As we keep increasing the number of students, we get a better and better estimate of what the mean is for these 20 schools. But only as we increase the number of schools do we get a better estimate of what the mean is for all schools. So the key thing is, again, we need to deal with each component of the variance separately. Increasing the number of students decreases this little piece over here. Increasing the number of schools decreases this piece over here. And in this particular example, where we had 20 schools and a total of 1,000 students, we ended up with this component of the variance being 35. This is 9.3. So the total variance is 44, as compared to up here in case A, where the total variance ended up being 10. Obviously down here, there's more error variance, the estimate is less precise, and so power is going to be adversely affected. We can also see how this works within the program. When the ICC was set at 0.07, which implies that in the population, the variance of school means is 700, we needed about 11 schools per treatment to get that part of the error variance down enough to get good power. If the ICC was higher, let's say we move the ICC up to 0.20, which would imply that the population variance at the school level, instead of being 700, was 2,000. In that case, power would go down to 63. We would need to increase the number of schools. We'd have to bring that up to about 21 per treatment to get power back up at 90%. On the other hand, if the ICC was down as low as, let's say, 0.02, then we could get by. We could reduce the number of schools and bring it down as low as 7 per treatment and still have power over 92%. So the key idea is that as the ICC goes up, so that the population variance between schools is higher, we need to increase the number of schools so that the error variance between schools stays at a reasonably low level. By contrast, as the ICC goes down, so that the population variance between schools is low, then we can get by with a smaller number of schools.